So in my previous class, I have completed the discussion of the solutions for the questions in the assignment in Center of Mass and Conservation of Linear Momentum up to the question number 53. So next today in today's class, that means in this class, I am going to complete the discussion of the questions, remaining questions, starting from question number 54 onwards. Look at the question number 54 on the screen. A person of mass capital M equal 90 kg, standing on the horizontal plane of ice, throws a body of mass small m equal 10 kg, horizontally on the same surface. The distance between the person and the body after 10 seconds is 10 meters. The kinetic energy of the person in joules is. So here, let V1 be the magnitude of the velocity of the body of mass small m, which is thrown by the person, along the ice surface. Let V2 denote the magnitude of the velocity gained by the person after the person throws the body along the surface. So we can consider the two masses capital M and small m as one system. The total weight of the system is balanced by the normal reaction forces by the smooth ice surface. So there is no external force acting on the system. Therefore, the total linear momentum of system of the two bodies remains constant. The final momentum system just after the person throws the body must be equal to the initial momentum system just before the person throws the body. Initially, both the person and the body are at rest. So initial momentum system is 0. Therefore, the final momentum must also be 0. The vector sum of the momenta of the mass capital M and mass small m must be 0. So vector sum of the momenta of the two bodies will be 0 when both the bodies are either at rest or move in opposite directions with same magnitude of momentum. So when the body is thrown horizontally along the surface, with some momentum, the person begins to move back with same magnitude of momentum. So final momentum of the system is equal to, can write m1 v1 bar plus m2 v2 bar. That is equal to initial momentum system. We can take it as 0. So m1 v1 bar equal to minus m2 v2 bar. You have to find the kinetic energy of person. That means you have to find v2. The two velocities are in opposite directions. Here m1 means mass of the body projected, that is equal to 10 kg. m2 is equal to capital M, that is 90 kg. So you can write v1 bar equal to minus 9 v2 bar. So that the two bodies move in opposite directions. So after 10 seconds, the distance moved by the mass small m is equal to magnitude of the velocity of the mass small m into time interval. The distance moved by the person in the opposite direction in the same time interval is equal to magnitude velocity of the person into time interval, and that is given to be equal to 10 meters. That means some of the magnitudes of the velocities of the two bodies will be equal to 1 meter per second. To simplify the previous equation, V1 is the modulus of V1 bar and V2 is the modulus of V2 bar. That means magnitude of the relative velocity of mass small m with respect to capital M will be 1 meter per second. So, but V1 in magnitude is equal to 9 times V2. The negative sign indicates that the two velocities are opposite. So when you consider the magnitudes, you can write V1 to be 9 times V2. You can substitute the value of V1 from second equation into the first equation. If you substitute the value of V1 from second equation into the first equation, 9V2 plus V2 is equal to 1 meter per second. To simplify this, you get V2 equal to 0.1 meter per second. So kinetic energy of the person of mass capital M will be half m into V2 square. That is half capital M is equal to 90 kg into V2 equal to 0.1 meter per second or 10 power minus 1 meter per second. So if you want to copy down the solution of the problem, you can take a pause and copy the solution of the problem. You can try to simplify this further. To simplify this, you get 0.45 joules. So for question number 54, which I just now discussed, the first option will be the answer. See the next question, question number 55. Two carts on horizontal straight rails are pushed apart by an explosion of a power charge Q placed between the carts. The coefficients of friction between the carts and the rails are identical. The 200 kg cart travels a distance of 36 meters and stops. What is the distance covered by the cart weighing 300 kg? So we can consider the two carts together as one system. Then we have to, it is understood from the description that the two carts are originally attached, so initial amount of system is 0. So final amount of system of the two carts just after they start moving, that is after explosion of this power charge Q, that means this is gets disconnected. The two carts get disconnected after the explosion of this power charge Q. So initial amount of system is 0. So the final amount of system is equal to vector sum of the momenta of the two masses. So m1 v1 bar plus m2 v2 bar. So m2 v2 bar equal to minus m1 v1 bar. The negative sign indicates that the two velocities v1 bar and v2 bar are in opposite direction. So when you consider the magnitude, the negative sign can be omitted. So here m1 you can take 200 kg and m2 equal to 300 kg. So if you take magnitudes, you get 3v2 equal to 2v1. If you don't put the bar symbol, they represent the magnitudes of velocities. So you get v2 by v1 equal to 2y3. Or v2 by v1 you can write, if you want to write in letter notation, m1 by m2. So you can apply work energy theorem for motion of each cart separately. If you apply work energy theorem for motion of the first cart after it begins to move, change in the kinetic energy is equal to work done by the resultant force, or change in the kinetic energy of the body is equal to total work done by all the forces. So change in the, let us apply work energy theorem for the first cart with mass m1 first. Change in kinetic energy for its motion is equal to final kinetic energy minus initial kinetic energy. The final kinetic energy after it travels 36 meters becomes 0. The initial kinetic energy for motion after it begins to move, when it starts moving, is equal to half mv1 v1 square, is equal to total work done by all the forces. That is work done by the frictional force plus work done by the gravitational force plus work done by the normal reaction. Here each cart moves in the horizontal direction. Therefore, no work is done by the gravitational force and no work is done by the normal reaction force. So total work done on the cart of mass m is equal to work done with the frictional force. The force of friction acts opposite to the displacement. Therefore, work done by the frictional force is equal to Fk into S into cos theta. Force of friction acts opposite the direction of displacement. Therefore, angle between the direction of the frictional force and direction of the displacement of the first cart is 180 degrees. So here minus half magnitude of frictional force on the cart of mass m1 is equal to product of the coefficient of friction into magnitude of normal reaction. Magnitude of normal reaction on the cart of mass m1 you can write m1g. Cos 180 degrees is equal to minus 1. So you get this S1 equal to V1 square by 2 nu k into g, or 2 nu g you can write otherwise. Just put small f here. Small f represents magnitude of friction. Nu is the coefficient of friction. Similarly, for second cart, similar calculation can be done for second cart. You can write by analogy S2 equal to V2 square by 2 nu g. In case you remember the conclusion I have discussed earlier in friction, you can directly write this step. Stopping distance. I discussed one special case in friction with small heading stopping distance. That means if a body starts moving with some initial speed u along a rough horizontal surface, then the distance it travels along the rough surface during the retarded motion under the action of its weight mg, normal reaction and friction forces is given by S equal to u square by 2 nu g. In case you remember that conclusion, you can straight away write this step. Similarly, for second mass, you can write S2 equal to V2 square by 2 nu g. If you divide this equation with this, you get S1 by S2 equal to V1 by V2 whole square. Coefficient of friction between each mass and the horizontal surface is same. V1 by V2 you can write from here magnitude of velocity of m1 to magnitude of velocity of m2 equal to m2 by m1. So m2 by m1 whole square. So that is 300 by 200 whole square. Now from this, if you simplify it to yourself, if you want to copy the solution of the problem, you can take a pause and copy the solution of the problem. So you get S1 by S2 equal to 9 by 4. S1 is 36 meters. From that you can find S2. Come on, copy down and complete the simplification part. In case you need more time to copy the solution, you can take a pause and take your time. So for question number 55, which I have just now discussed, the third option is the answer. Next is the question number 56. Two bodies of mass m1, m2, m1 greater than m2, respectively, are tied to the ends of a string which passes over a light frictionless pulley. The masses are initially at rest and then released. The acceleration center of mass is. So, this problem comes under one case which I have discussed in Newton's laws of motion at Wood's mission. So when the two masses are released from rest, the heavier mass m1 starts moving vertically downwards. The lighter mass m2 starts moving vertically upwards. At A1 bar with the acceleration of the mass m1 and A2 bar with the acceleration of the mass m2 in vector form. A1 bar is directed vertically downwards, A2 bar is directed vertically upwards. They are in opposite directions. As we have discussed with this case in Newton's laws of motion, I don't want to repeat the calculation of magnitude of acceleration of each mass. You must be able to calculate the magnitude of acceleration of each mass, which we discussed in Newton's laws of motion. So magnitude of A2 bar is equal to magnitude of A1 bar. Magnitude of acceleration of each mass is given by m1 minus m2 by m1 plus m2 into g. So in vector form, we can write A2 bar equal to minus A1 bar. So acceleration of center of mass of the system of the two masses is given by m1 A1 bar plus m2 A2 bar by m1 plus m2. So you can now substitute here A2 bar equal to minus A1 bar. So you get the acceleration of center of mass in vector form equal to m1 minus m2 by m1 plus m2 A1 bar. Because m1 is greater than m2, m1 minus m2 is positive. Therefore, the ratio m1 minus m2 by m1 plus m2 is a positive scalar. As you know, if vector is multiplied with a positive scalar, you get another vector which acts in same direction. Therefore, direction of acceleration vector of center of mass of m1 and m2. That is the direction of the acceleration center of mass system of the two mass m1 and m2. Same as the direction of A1 bar, which is directed vertically downwards. Therefore, you can say that the acceleration of center of mass of system of the two mass m1 and m2 will be directed vertically downwards. In case you are asked direction also. So if you take modulus now here both the sides, mod of ACM bar equal to m1 minus m2 into mod of A1 bar. Mod of A1 bar you can substitute it as equal to m1 minus m2 by m1 plus m2. Mod of A1 bar you can substitute m1 minus m2 by m1 plus m2 into g. So magnitude of the acceleration center mass of system of the two masses will be equal to given by m1 minus m2 by m1 plus m2 whole square into g. So that's the answer. In case you want to copy the solution of the problem, you can take a pause and copy the solution of the problem. So for question number 56, third option is answer. Which I just now discussed For question number 56, third option is the answer. See the next question, question number 57. This was originally given one of the previous IIT papers. Think in 2009 or somewhere. Don't exactly know the year, but near recent years only. So look at the diagram given in the figure, which has been drawn with ink of uniform line thickness. The mass of ink used to draw each of the two inner circles and each of the two line segments is small m. The mass of the ink used to draw the outer circle is 6m. The coordinates of centers of the different parts are outer circle 0, 0. So let us denote the mass of the outer circle by m1, which is equal to 6m. The coordinate x coordinate is 0, y coordinate is 0. The left inner circle, which one? The left inner circle has mass m. And the coordinates of the inner circle, left inner circle, are given to minus a comma minus a. So x2 we can write minus a, y2 equal to a. For the right inner circle, for this, the coordinates are a comma a. For right inner circle, denote the mass m3. This is m2. This is m1. The right inner circle, the mass is m. The x coordinate is a, y coordinate is also a. For vertical line, this one, the mass is m4 equal to m. The vertical line is at 0, 0. Center of mass of vertical line is at 0, 0. That means x coordinate x4 is 0, y4 is 0. And this horizontal circle, and each of the two line segments, there are two line segments. One vertical line segment is 0, 0, and other line segment is here. That we denoted by mass m5, suppose. The mass m5 for the horizontal line segment is also equal to m. The x coordinate is 0, y coordinate is minus a. You are asked only y coordinate center of mass. So y coordinate center of mass of the system of all the masses, can write m1 y1 plus m2 y2 plus m3 y3 plus m4 y4 plus m5 y5 divided by m1 plus m2 plus m3 plus m4 plus m5. So if you want to copy the solution of the problem, you can take a pause and copy the solution of the problem and try to complete the simplification part yourself. Substitute all the values which are written on the left side and the equation on the right side and simplify it yourself. And take a pause and complete the solution of the problem. So for question number 57, which I just now discussed, the first option will be the answer. Next, see the question number 58. An isolated particle of mass m is moving in horizontal plane, that is xy plane, along the x-axis at a certain height above the ground. Suddenly explodes into two fragments of mass m by 4 and 3m by 4. At an instant later, the smaller fragment is at y equal plus 15 centimeter. The larger fragment at this instant is at. You have to find the y coordinate for the larger fragment of second fragment. Isolated particle means you can assume that the external force on system is 0. If the external force on the system is 0, the velocity center of mass of system remains constant. So initially center of mass is moving along x-axis at a constant height above the ground. Therefore, we can assume that center of mass continues to move at the same center of mass system of mass m continues to move at the same vertical height above the ground. That means y coordinate center of mass will remain constant. So y coordinate center of mass system in second case, same as the y coordinate center of mass system in the first case. Initially it is moving along x-axis, so initial height of the center of mass above the ground is 0. I mean y coordinate. Initial height of center of mass above x-axis, not from ground, above x-axis 0. That means because center of mass is initially moving along x-axis, so you can say initial y coordinate center of mass 0. So y coordinate center of mass in second case equal to m1 y1 plus m2 y2 by m1 plus m2. So from this you get m1 y1 plus m2 y2 equal to 0. So you simplify this yourself, you get y2 equal to minus m1 by m2 into y1. M1 is the mass of the first smaller fragment, that is m by 4. M2 is the mass of the other part, that is 3m by 4. So I get y2 equal to minus y1 by 3. y1 is the y coordinate for the lighter fragment, that is 15 centimeters. So the y coordinate for the other mass, you get heavier mass minus 5 centimeters for the larger fragment. If you want to copy the solution of the problem, you can take a pause and copy the solution of this problem. So for question number 58, which I have just now discussed, first option is the answer. So then look at the question number 59. A small sphere of radius r is held against the inner surface of larger sphere of radius 6r. The masses of large and small spheres are 4m and m respectively. This arrangement is placed on horizontal table. There is no friction between any surfaces of contact. The small sphere is now released. Find the coordinate center of mass of larger sphere when the small sphere reaches the other extreme position. So here, there is no friction here between the large sphere and the horizontal surface on which it rests. The external force acting on system are the weight of the system, which acts vertically downwards. Normal reaction force by the horizontal table on the large sphere acts vertically upwards. So, which balance each other. Therefore, there is no external force acting on system. Therefore, velocity center of mass of system remains constant. As no external force acts on system, the velocity of center of mass of the system remains constant. Initially, both the spheres, small sphere and large sphere, are at rest. They are released from rest. So initial velocity of each sphere is 0, therefore initial velocity of center of mass of sphere also 0. And velocity of center of mass remains constant. That means velocity of center of mass remains 0. Or you can center of mass of system of the two spheres is at rest. I mean there is no displacement for center of mass system of the two spheres in the horizontal direction. I mean at rest in the horizontal direction. I mean, or you can say this way, the x square and the center of mass of system of the two spheres remains constant. Because there is a horizontal component of the external force on the system is 0. Horizontal component of velocity center of mass remains constant. That is 0. So x square and center of mass of system remains constant. Because center of mass of system of the two spheres will not be displaced in the horizontal direction. Because there is no external force acting on system in the horizontal direction. There is no external force acting on system in the horizontal direction. Therefore, horizontal velocity center of mass remains constant, and which is equal to 0. Therefore, horizontal coordinate or x coordinate center of mass remains constant. So you can write, you can take the first mass m1 equal to the large sphere, that is 4m. In the first case, x coordinate of large sphere in the first case equal to, as shown in the figure, that is equal to L. Y coordinate is 0. So for second mass m2, which is the mass of small sphere, what is the initial value of the x coordinate? From here to here, this is L. So this is the radius of the bigger sphere. The radius of smaller sphere is R. The radius of bigger sphere is 6R. Don't try to measure with the scale and don't say that it's not tying. The diagram is only drawn roughly. So this is understood to be 6R. So this distance between the center of large sphere, I mean initial distance between the center of large sphere and center of small sphere, will be 6R minus R. That will be equal to 5R. So x coordinate of small sphere in the initial position is equal to L plus 5R. So when the bigger, you have to find the x coordinate of the, of course y coordinate is 0 in the initial condition. So when small sphere comes to the other extreme position, center of each sphere will be on x-axis. So center of mass, y coordinate center of mass will be y1 is 0, y2 is 0, therefore y coordinate center of mass will be 0 in the initial position. So in the final position, draw a rough figure. When the small sphere goes to the other extreme position, you have to find the x coordinate center of large sphere. That means new value of the x coordinate of the first mass, which we denoted by x1 dash. This radius of large sphere is 6R. Radius of small sphere is small r. So this is the x coordinate for small sphere in the new position, which we denoted by x2 dash. we have to relate x2 dash. So this distance between, the distance between new position of center of small sphere and center of large sphere will be 6r minus r. That will be 5r. You have to find x1 dash. So x2 dash, you can observe from the figure, x2 dash plus 5r equal to x1 dash, or x2 dash can be written as x1 dash minus 5r. Now we can write x square and the center of mass system of the two spheres in the new position, xcm dash, same as x square and the center of mass system of the two spheres in the original position. So x square and the center of mass in the new position, you can write m in the original position, m1 x1 plus m2 x2 by m1 plus m2. The new value of x square and the center of mass will be m1 x1 dash plus m2 x2 dash by m1 plus m2. So m1 plus m2 can cancel. Can write here now m1 equal to 4m, x1 equal to l on the right side, m2 equal to m, and x2 equal to l plus 5r. On the left side, substitute x2 dash equal to x1 dash minus 5r. Because you are asked to find x1 dash here. So those who want to copy the solution of the problem, they can take a pause and copy the solution of the problem. Not only just copying the solution of the problem, try to complete the simplification part yourself carefully. So you can substitute here m1 equal to 4m and x1 dash you have to find m2 equal to m, x2 dash you can write x1 dash minus 5r. On the right side you can write m1 equal to 4m, x1 equal to l, m2 equal to m, and x2 equal to l plus 5r. Come on, copy down and complete the simplification part yourself. In case you need more time for completing simplification part, you can take a pause and take your own time. So if you simplify that, you get x1 dash equal to l plus 2r. That is the new position of x coordinate of center of large sphere will be l plus 2r. Of course, y coordinate of the center of large sphere will remain 0. Because the center of each large sphere moves only in the horizontal direction. It will not move in the vertical direction because the large sphere is resting on a horizontal table. So y coordinate of center of large sphere will be 0. So the answer for this question, which just now have discussed, will be l plus 2r comma 0. Look at the next question, question number 60 here. If there is no external torque on an isolated body about its center of mass, then the velocity center of mass remains constant. Statement 2. The linear momentum of an isolated system remains constant. So here, it's a statement, if no external torque acts on system about its center of mass, we can say that angular momentum system about center of mass remains conserved. That will be discussed later in rotational mechanics. But here there is no external torque about its center of mass does not mean that the net external force on the system is 0. Therefore, we cannot conclude that if the net external force on system is 0, then velocity center of mass remains constant. But if the net external torque about center of mass is 0, does not imply that net external force on the system is 0. Therefore, you cannot conclude that velocity center of mass remains constant when there is no external torque on the system. Therefore, statement 1 is false. The linear amount of an isolated system remains constant. That is true. Isolated system is when the external force on the system is 0. Total linear amount of system remains constant. Therefore, statement 1 is false and statement 2 is true. So with this, I have completed the discussion of all the 60 questions in the assignment in center of mass and conservation of linear momentum. So some of the students may not be able to solve the problems from assignment in their first effort when they try these questions first time. So you should not feel discouraged here. Every student can improve. The student wants to improve seriously. So in case you feel that you are very poor and you are unable to get any idea for solving most of the problems, I mean, in case you don't get any idea how to solve most of the questions, when you read those questions for the first time, observed with good number of students that most of the students, they get frightened by looking at the questions in physics. So you can do like this. In case you are unable to solve most of the questions in the assignment, when you try for the first time, you can do this way. If I go through all these solutions for all the questions, one after another. Going through the solution does not mean just reading the solution. You must keep working on paper simultaneously. Next, they can take a gap, time gap, or the for gap of 1 hour or 1 day. Then again, they can start trying the questions from assignment starting. That means they must start afresh again. Again, they must start going through all the questions in the assignment starting from question number 1. Again, they can start trying one by one all the 30 questions in each assignment. That means after going through solutions, they can take a gap of 1 hour or 1 day. They can again try these questions. They should try to work out the assignment again because already they have gone through solutions earlier. They will now be able to solve most of the questions when they go through assignment for second time. So finally, they should be able to solve the problems of the models discussed in this assignment in case the same questions or same model questions come in the entrance examinations. Okay. We'll continue discussion next